So in general, if we have the equation y prime equals a y for n equals 2, where that means that the y vector is a column vector with 2 components and the A matrix is a 2 by 2 matrix. If we get we generally get 2 eigenvalues, lambda 1 and lambda 2. Sometimes those eigenvalues are real, sometimes they're imaginary, sometimes they're complex, but sometimes they're equal. So if the two are equal, we can get an eigenpair for the first of the two. Of course, they're equal, so it doesn't matter if we call it the first or the second, but let's just say we get an eigenpair for lambda 1. And solving the equation, we get the eigenpair by solving this equation with this condition. That gives us the eigenpair, gives us a solution y1 equals e to the lambda 1 t x1. That is a solution of the system. To get a second solution, we can't use the same value with the same process, so we assume another solution y2 of the form t e to the lambda 1 t v1. You see that 1 is kind of smushed up, as is this one. Remember, if it's a 1 or a 2, it doesn't make any difference because the two are equal. But anyhow, those are intended to be 1s. E to the lambda 1 t v1, t e to the lambda 1 t v1 plus e to the lambda 2 v2. Just the same as the solution we assumed previously. We're just generalizing the process. And we take the derivative, which just means we take the derivative of this function using the product rule and this function just using the chain rule. And that yields, now let's go back. The equation is y2 prime equals a y2. So this first solution is multiplied by a, and that gives us a y2, and it should be very clear that a y2 will just equal this, factoring out the scalars, and that y2 prime equal this is equal to a y2. So setting y2 prime here equal to a y2 in this expression, we see that every term has the common factor e to the lambda 1 t. We can divide that factor out since it can't be 0. And that leaves us with what? The v1 here, the lambda 1 t v1 here, the lambda 2 v2 here, the t a v1 here, and the a v2 here, giving us this equation. As we did with the specific example before, we note that the factors of t have to be equal. They are the coefficients of t on both sides have to be equal, so that lambda 1 v1 has to equal t a v1, and that implies that this lambda 1 t v1 has a t on it. I wrote the t here. I'm going to get rid of that. On second thought, I'm just going to write the t here. It's out of order, but that won't hurt anything. If we divide by t and bring everything on the same side, this becomes a minus lambda I v1 equals 0. And then what's left without the coefficient t is, we'll write it out in the order it appears, v1 plus lambda 2 v2 equals t, we don't have the t, equals a v2. And I'll get rid of that t. And then this equation rearranges, bringing the v2 terms onto one side. We see that we have a minus lambda v2 And I wrote that wrong because I was looking at something else. Now things make more sense. My original error was to write a V2 here where it should have been A minus lambda I times V2. And that's what we get on one side, and we get V1 on the other. Very similar to what we got before. Other things that I noticed, I had a lambda 2 up here and a lambda 2 here. That technically wouldn't have been wrong because lambda 1 and lambda 2 are identical, but it kind of confuses the issue. And since I'm putting 1s on all my lambdas, I'm going to do it here and here as well. Now, again, this is actually fairly simple. You might not have seen what to do originally, but it's fairly easy to follow. We start with our equation, assuming identical eigenvalues, we get one solution. Then we assume a second solution that's a multiple of the first, or a multiple of some vector plus another multiple of another vector, manipulating the coefficients of those vectors in a way that's sort of motivated by what we did with systems of a single, second order linear equations of a single function. Taking the derivative, etc., we set the derivative equal to the product of the matrix and the vector, and we get this equation. Setting the t terms equal, we get this equation which rearranges to this. Setting the remaining terms equal, we get this equation which easily rearranges to this. A minus lambda 1I V1 equals 0 can be solved with the eigenvector x1 obtained from the same equation up here. And I suppose that I should put subscripts on those lambdas as well. And the equation is degenerate and can be solved in the sense that we can find vectors V2 that satisfy it. And all we have to do is plug in our x1 here and do what comes naturally, do what's obvious. That's fine if n equals 2. If n equals 3 or more, things can get a little bit complicated, and we need to talk about that for a few minutes.